This is Sriram's fourth time presenting at NANOG. Sriram's first talk at NANOG was called BGP Anomaly Detection and Robustness Algorithms way back at NANOG 43 in Brooklyn, New York in the year 2008. Welcome back to NANOG, Sriram. Appreciate you being here, and it's a pleasure to have you back with us today.
Thank you for the kind introduction. Good afternoon, everyone. So I'm here today to share with you about the ASPA, Autonomous System Provider Authorization, an RPKI object, and how this object can be used in the routers to do AS path verification and route leak detection mitigation. There are many folks, authors on 3 different ASPA drafts that are progressing quite nicely through the IETF. So I want to acknowledge all the authors on those 3 drafts, and also several other people who are doing implementation and very actively, a lot of people participated in the working group last call discussions on these drafts. So a lot of good feedback was received from the community, and that's been folded into revising these drafts. So they are hopefully in good shape. So today I will mainly focus on one of them, the path verification draft. I was going to give a little brief on like basics of BGP and BGP hijacks, RPKI, ROV, etc. But yesterday, Alistair did a very good job of summarizing all of that for us here. So I'm going to skip some of those slides and move forward. But essentially, I will explain what ASPA is and how it can be utilized for path verification and route leak solution. So I'm skipping a few slides that relate to BGP hijacks, RPKI, ROA, etc. So even if you have the solution for route hijacks using RPKI, we still have the problem of forged origin prefix hijacks. So that is essentially a path manipulation. So in this picture, ASA originates prefix P and it makes its way through multiple hops to ASD. So ASD has available the legitimate path. At the same time, a determined hijacker is doing what we call a forged origin prefix hijack. What that means is that the hijacker inserts the the AS in the ROA of the prefix P with ASA. So from that ROA, they take the origin AS, the legitimate origin, insert it into the path, and announce it. When that reaches ASD, it is unable to distinguish. It does the RPKI route origin validation, and it is unable to distinguish between the two routes in terms of ROA validation. They both are valid because of the forged origin. So this is a problem that we call forged origin prefix hijack. And the solution to this, of course, we have the solution in BGPsec, where every AS, so origin AS, there would be a ROA for the prefix with the originating AS, and then every AS would sign the path to the next AS. And when AS5 in this picture receives the correct path, it is able to verify all the signatures, and it can verify that that's a valid path. And if AS6 tries to fake a connection to AS1 and sends a shorter route to AS5, it would not be successful. It would not be successful with that forged origin announcement because it doesn't have a signature from AS1. So BGPsec certainly is a solution for forged origin. But we then have ASPA, which would also provide a solution for that in part, not entirely, but in in part. So we will look at that, and ultimately we would hope that, but of course I should also mention that BGPsec does not solve the problem of route leaks. So we do need ASPA to solve route leaks, and at some point in the future, perhaps ASPA will come into deployment sooner, and then BGPsec will follow later. But ASPA would be able to solve the route leak problems, and also to a certain extent, it would be able to solve the path manipulations or forged origin hijacks, things like that, partially, not entirely. We will go into the details of those in the rest of this talk. So let us begin by looking at what it means to say that there is a route leak. So in this picture, my employer NIST network is on the left, with originating its prefix P, and this is a picture only for illustration, not depicting real connections in the real world. So let's say NIST is connected to CenturyLink, and CenturyLink is peering with another major or tier 1 type of ISP, that is ASA. And on the right-hand side, there is broadband provider, LTE 5G network provider, and millions of users are present there. And let's say that there's a major workshop going on at NIST, and many users are connected to NIST attending the workshop. And suddenly a route leak happens from XYZ Pizza AS64500 at the bottom. So they have taken the NIST prefix and maybe perhaps other prefixes and accidentally perhaps leaked them to ASA. If ASA doesn't have the route leak detection capability, it would accept it, install it, and then propagate it. In that case, many of these users currently in the workshop with NIST, their traffic would try to detour through XYZ Pizza, and it will get dropped on the floor because the XYZ is not able to carry that kind of traffic. So whenever you have a violation of what we call valley-free, the route should be valley-free, and if the route is not valley-free, as you can see in this picture, the route went down towards a customer, and then the customer from CenturyLink, it went down towards XYZ Pizza, and XYZ Pizza propagated it up towards another transit provider. So that is a violation of valley-free. So when that happens, the large amount of traffic will try to detour through that AS, and it would not be able to carry the traffic, and there is a disruption of service. So the idea is that in the internet, we would like the traffic to move from low capacity network to higher capacity networks to even higher capacity networks, and then gracefully come down the same way to reach its final destination. So it's similar to like having a wrong sign on the highway pointing to an exit, and then a lot of traffic gets off the highway and goes on to local roads and experiences severe congestion. Route leaks occur frequently, several route leaks on a daily basis. There are measurements and incidents that are reported frequently. So looking at route leaks in a little bit more detail to try to understand what it is. These 4 pictures in this slide. In these pictures, what we are showing is that the route starts from AS1 originates prefix P, and then it goes through 2 to 3 to R being the receiver. And in the top 2 pictures, the route propagated from a provider to a customer from 2 to 3, and then it made a route, and then there is this route leak. 3 is leaking it and sending it to another provider or a lateral peer. And the 2 pictures below, it is a route goes on a lateral hop from 2 to 3, and then from 3 to 3 to R, it either goes on another lateral hop, which is a route leak, or it goes on a hop from 3 as a customer to R as a provider. So whenever you have the route propagating from if it's received from a provider or lateral peer, and it is propagated to another provider or a lateral peer, that is a route leak. So these are 4 typical path trajectories that are route leaks. And the trajectories that are not route leaks, they usually would consist of a ramp. Looking at the top, the 2 figures on the upper right side, you have an up ramp on the left and you have a down ramp on the right. And in between, you may have a hop or there is no hop. So it's a perfect inverted V, or it is a inverted V with a lateral peering hop at the top, like what we have here between 3 and 4. So these 2 paths are route leak free. So once an update starts from somewhere, it can go multiple hops, customer to provider, and once it makes a turn and goes towards a lateral peer or a customer, subsequently it should only be going from a provider to a customer down, down, down direction. If that doesn't happen, then there is a route leak. And the other pictures here are basically about, you can have only the left ramp, then it's not a route leak. You can have only the right ramp, then also it's not a route leak. So there are these trajectories that are not route leaks. The ASPA drafts I mentioned, there are 2 in particular, the ASPA verification and the ASPA profile, and we'll look at those today. There is a third one that is an extension of RFC 8210 in order to include ASPA PDU in it. That is the RPKI to router protocol draft, and that has also been updated to include the ASPA PDU. So these are the 3 drafts that constitute what's in progress with ASPA. So from the profile draft, one can draw this simple picture to explain what ASPA is. Again, ASPA stands for Autonomous System Provider Authorization. So this is an RPKI object. Any AS can create this and put it in the RPKI repository. So it's a signed object using the RPKI. In this case, customer I lists provider J, K, and M as its providers, transit providers. And these ASPAs are registered and stored in the RPKI registries. In the verification draft, we define these BGP roles. Those are provider, customer, lateral peer, IXP route server, RS client, and mutual transit. Of these, the customer and the IXP route, the route server client, they would create the ASPAs. Also, the mutual transit ASS would create ASPAs showing each other as the provider. So RS client RS to RS client relationship is essentially like a provider to customer relationship. Therefore, the RSAS would be included in the RS client's RS client ASS ASPA. And if a provider like tier ones, if an AS doesn't have any providers, then it would register what we call a AS0 ASPA. It means that the ASPA would contain only an AS0 as the provider. So in terms of what ASPA path verification is capable of, it can detect and mitigate route leaks and also improbable or infeasible AS paths. It can also detect forged origin prefix hijacks to some extent. It can detect forged origin path segment prefix hijacks also to some extent. We will describe how that works later on in slides 40 and 41. So for route leaks, it's very good. In terms of limitations, the ASPA method has limitations with regard to some forms of malicious AS path manipulations, and that too mainly when a transit provider attacks its own customer with path manipulations. And we'll see that in an example and on slide 43. But for the most part of this talk, we will focus on the route leak detection using ASPA. So in this picture, what we are seeing is 3 ASs, AS1, 2, and 3. AS1 propagates a route to AS2, and AS2 leaks it to AS3. So these are the 4 cases where the route is received from a provider or a lateral peer, and it is leaked to another provider or lateral peer. Each of these is obviously a route leak. How does ASPA detect that any of these is a route leak? So in this case, if AS1 simply has an ASPA stating that AS5 is my provider, they list AS5 as a provider. In that case, AS2 is not a provider, therefore AS2 is either a customer or a lateral peer. So when AS3 looks at this path, AS1, AS2, it knows that AS2 is receiving it from a customer or a lateral peer. And in each of those cases, if AS1 to AS hop is not a customer to provider hop, it is a route leak. It involves one of those valleys in the route. So all that is needed in this is AS1 to have an ASPA that lists its provider, and that doesn't include AS2 as a provider, and AS3 is readily able to detect that it is a route leak. Okay. Slow. Okay. In order to proceed with describing the algorithm for route leaks, we need the help of what we call ASPA hop check function, and this function is utilized in the algorithms. The way it is defined is if we have ASI connected to ASJ, we would use ASPA to determine the validity or the hop check function of I to j. If ASJ is included in the ASPA of I, this hop is a provider. It is attested provider by ASI. And if it is not included, if j is not included in the ASPA of I, then it is attested not provider, in which case it is either a lateral peer hop or a provider to customer hop, either the horizontal or down. And in the third case, if there is no attestation, if ASI doesn't have an ASPA, then this hop is not attested, which means that it could be up, down, or lateral. We are not able to distinguish between those. So the path could be from a customer to a provider, or lateral peer, or from a provider to a customer. So that's the definition of hop check function. In the notation that you will see going forward, we have what we are doing is we are doing a little simplification. It's a sequence of ASs, 1, 2, 3, 4. And for simplicity, we just denote, and these ASs represent the unique ASs in the path. For simplicity, we represent them as 1, 2, 3, 4. 1, 2, 3, 4 don't mean that they are the AS numbers. They simply mean the position of the unique AS in the path. So we have two types of verification, one for upstream paths and another one for downstream paths. We call it an upstream path when the update is received from from a customer or a lateral peer. So in this case, the verifying AS is receiving it from a lateral peer, and the path is 1 to 2 to 3. If we look at the ASPs, we make use of the hop check function that we just defined, and we determine the hop check function for 1 to 2 and 2 to 3. And if each of these hops checks out to be a provider, then the path is route leak free, it is valid. On the other hand, if the path is, say in this example, 1, 2, 3, 4, the verifying AS is validating that path, and it uses the ASPA, computes the hop check functions, and what it sees is that there is at least one hop in the path which is not provider, which means that the path made a turn downward. From 3, it started to go down or lateral. After that, it should only be going down from provider to customer, and that's not happening. 4 is sending it to a provider up. So that's how, by using the ASPA, the verifying AS is able to tell that it is invalid or there appears to be a route leak. So the algorithm based on what I just described is simple. If there is no hop in the AS path, if every hop in the AS path is provider, customer to provider, then the route is valid. If at least one hop is not provider, which means that it already made a turn downward, and then later it is going up, so that constitutes a route leak, and that would be invalid route. And if none of those, then the path is determined to be unknown, which means that we don't have enough ASPs to tell if it is valid or invalid. And as I said, we have upstream path verification and downstream path verification. So this next set of slides is regarding the downstream path verification. First, we focus on invalid. So receiving AS on the right-hand side is receiving this AS path 1 to n. These are unique ASNs, unique ASs. And in this path, what we look for, or what the router looks for in the algorithm, is whether or not the following is true. It looks for ASI on the left, and the hop from I to I plus 1 on the left, and on the right it looks at hop j plus 1 to j. For any I and any j, if it is true that I to I plus 1 is not provider, and j plus 1 to j in the opposite direction to the route propagation, if that is not provider, then this is a route leak. So this is the classic definition of route leak. The path propagated on the left on a peer-to-peer lateral peer link, or from provider to customer, and then it is propagating again later, somewhere later in the path, maybe the adjoining hop, but it is propagating on the right side from a lateral peer to lateral peer again, or it is propagating up from customer to provider. So that is the classic definition of a route leak, and therefore the path would be determined as invalid. So in this, essentially the ASPA is used to determine whether or not this happens. If it does happen, only 2 hops are enough to tell that it is route leak. So if for any 2 hops with j greater than I, if this turns out to be true, then this is a route leak. For validity, as I've already said before, if you have a perfect inverted V, the route is a perfect inverted V, or if it is a V with one lateral hop at the apex, in those cases, the path validation outcome would be valid. And again, the algorithm is looking for an up ramp on the left, customer to provider, up, and it's looking for a down ramp on the right side, down, provider to customer. So if it finds those, and at the apex points, so this is using again ASPA and the hop check function. At the apex between 3 and 4, if there is one hop, that is still okay, and if there is no hop at the apex, there is a single node at the apex, that is also fine. So in those 2 cases, path is valid. So if we have been able to determine that either the path is invalid based on this, or valid based on this inverted V establishment. If we haven't been able to do either of those, then the outcome is unknown, which means that we don't have adequate ASPAs to be able to tell whether the path is valid or invalid, route leak or not route leak. So that is a summary of the upstream algorithm and the downstream algorithm for determining the AS path validity, and also whether or not there is a route leak. So what we do in the next few slides is, if someone is interested to look at the formal proof of this algorithm, that is what offered over the next few slides. I'm not going to go through that. Just wanted to include the slides so someone can look through it, and the proof is, but the proof basically uses some combination of combinatorics and geometry to show that take all the possible trajectories. You're applying ASPA. It makes possible certain set of trajectories, and out of those trajectories, whether or not you can tell definitively the path is valid or invalid. So going through that, we have a couple of theorems, and we write down the algorithm which is included in the draft. So, but the algorithm is essentially what I described for the upstream and the downstream. So now we turn our attention to what is still left to do with in this. One thing we realize is that ASPA is not able to do a detection of a local route leak. If an AS receives a route from a provider or a lateral peer, and how would it make sure that it itself doesn't send it on the egress side to another provider or lateral peer? So in order to be able to do that, ASPA doesn't provide us that capability. It allows us to be able to detect the route leak somewhere else in the path. But at my own AS, I need to make use of RFC 9234 to be able to detect that. And the way that is done is there is this OTC attribute. The OTC attribute is added on the ingress to eBGP, and that is when a route is received from a provider or a IXP route server or a lateral peer. And if the OTC attribute is present on the egress side, I would not send it to another provider or a lateral peer. So that is how the local route leak is prevented using RFC 9234 or the OTC attribute. OTC stands for only to customer. So now we'll highlight a few key properties, and with that we will wrap up the presentation. These properties are definitely encouraging for early adoption. So they are pretty good early adoption incentives. For key property descriptions, next 5 slides, we are assuming here that malicious AS path manipulations are not involved, especially removal of certain ASs from the AS path. We'll look at that later in slide 43. That is a limitation of ASPA. But what we are going to highlight are properties that relate to route leak detection and forged origin prefix hijacks. So this property 1, let's say that only 2 ASs are doing ASPA in the entire internet, ASA and ASB. If a route propagates from ASA and goes towards a customer or a lateral peer, and then it is leaked somewhere along the path and it is received at ASB from a customer or a lateral peer, ASB is always able to detect the route leak. So that's a pretty good early adoption incentive. A corollary of that is that if most major ISPs are ASPA compliant, the propagation of route leaks in the internet will be severely limited. The second property is regarding forged origin prefix hijack, because so ASX is trying to hijack a prefix originated from ASA, and it is inserting the false origin ASA into the route. However, that would not be successful if ASA ASA has an ASPA because it is showing the set of providers it has, and ASX is not one of them. Therefore, at ASB, when it receives the two routes and does the validation using ASPA, the route from ASX will come out invalid. So that is the protection against forged origin prefix hijack. Then also there is a forged path segment prefix hijack. What that means is that the attacker now tries to get smarter. They look at the ASA and say that, oh, it has an ASPA, so okay, let me include one more ASB also in the path before I attach my own ASX. And that would also not succeed if both ASA and ASB have ASPA, because ASB's ASPA does not include ASX as a provider. So when ASD receives it, it would be able to determine it as an invalid path. And if we have a ASP island, then naturally any route that is propagated within the island would be free of route leaks, because every AS is doing ASPA validation and route leak detection. This is my final slide. So I have been talking about path manipulations, and ASPA doesn't address path manipulations partially, but not fully. BGPsec would be the way to tackle that. But this is an example of the path, malicious path manipulation. In this picture, every AS is doing ASPA, including the offender AS4. Now, AS4's customer is AS5. AS5 receives, normally it should receive two routes, one from AS4 and another from AS6. It is multi-home to two providers, and it should receive two routes, one from each of them, for the prefix P on the lower left-hand side. Now, AS4 is the offender, and it tries to play it smart by reducing the path length. It manipulates the path and pretends that it is connected to 2, and it propagates a shorter path to 5, possibly to attract 5's traffic away from its competitor 6. That could be a motivation. Whatever the motivation, if this attack happens, AS5 can be fooled. It is doing ASPA path validation, but it is not able to tell that one of the paths, AS4's path, is manipulated. So that's a shortcoming, and it can only happen in the downstream direction when a provider attacks its own customer. Hopefully that will be rare. And also we should realize in this picture that 4 is not intending to drop the traffic on the floor. It doesn't want to perhaps lose the customer. If it intends to propagate the data traffic towards its destination, whichever path it chooses, because everyone else is doing ASPA, it would only be the data traffic will only propagate to the destination from 5 only on route leak free paths. So that's another observation that one could make. So with that, I'll stop and take any questions you may have. Thank you.
Maria, the developer of BERT, please could you put there the previous slide? If every ASs are doing ASPA, isn't the shorter AS path ASPA unknown then?
Every AS is doing ASPA, including the attacker 4. Every one of them is doing ASPA.
Yes. So yes, I see. So but this means that the AS number 2 is not pairing with AS number 4, and then it means that AS number 4 must fake even in the ASPA that 2 is his provider.
Oh, okay, excellent question. So that has to do with the validation algorithm, how we validate.
Yeah.
So your observation is entirely correct. 2 has included 3 in its ASPA, but not 4.
Yeah.
But when 5 is doing the validation, in the path is 1 to 2 to 4 to 5, right? So the path is 1 to 4. And if we go back and look at this slide. See, in this case, 3 would have an ASPA, but it would not include 4 because 4 is a lateral peer. And, but still the path is valid because at the apex, the route is allowed to travel 1 hop laterally and then start to go down. So that is built into the algorithm. So 1 hop is allowed to be lateral at the top, at the apex. And so heading back to the slide we were on. Oh, sorry. So that is part of the algorithm, and that is part of the definition of what is valid and what is route leak. And it turns out that in this case, 2 to 4, 4 is at liberty, unfortunately, to pretend that 2 is a lateral peer or a customer or something. So 2 has not included 4. That by default means that 4 is not a provider, but it is a lateral peer or a customer, and that is allowed. In that case, the path algorithm determines it to be valid.
Yeah, so this basically means that 4 must sign the ASPA that includes 2 as the 4th provider. So then the AS path would look like the 2 is the top, the root of the tree. 1 to 2 is up, and 2 to 4 to 5 is down.
Yeah,
then
so
the ASPA would be valid. Yeah.
Yeah, you are on the right path in terms of trying to improve ASPA, but there are difficulties with what you are proposing. If you are proposing that there should be some kind of an arrangement to also have an object that certifies or registers lateral peers, customers, etc. So you can so ASPA definition right now only includes providers, but if you were to modify it to also have objects that would register lateral peers or customers, then you're right, this problem can be solved. But there is a difficulty with that runs into a contradiction. I mean, it runs into a problem for the algorithm, because once you allow those objects, the attacker can misuse those objects and try to prevent the detection of route leaks. So that we have explained somewhere else, but that indeed is what happens. So there is this limitation that at the apex of the route that is valid, you are allowed to have 1 lateral peering, and that is what 4 is taking advantage of.
Yeah, I see. I just wanted to find a clarification of this specific situation because I'm right now implementing the ASPA, so I'd like to see what's happening there, how to break it, and how to do it correctly. Yeah, thank you for clarification.
Can I catch you after the talk? I would love to talk to you. Thank you.
Hi, Mingwei Zhang from Cloudflare. So in your earlier slides, you mentioned that you're expecting ASPA to be deployed before BGPsec can be widely deployed. And as I understand, right now ASPA is still a draft. And I remember there's some discussion about making changes to the algorithm or to the recommended implementation for ASPA. So can you kind of explain why you think ASPA can be deployed earlier, and also kind of what's your opinion on the roadmap for deploying both ASPA and then BGPsec in the near future?
Okay. For the roadmap, Job Snijders has a blog and also a post in Nanog providing his view of the roadmap. But I also concur with what he's generally observing. Because BGPsec involves signatures on the path in the BGP update, that is intensive for the routers. So it requires special changes to the routers to facilitate verifying the signatures, signing the signatures, and forwarding. So that is why although the RFC has been around for about 5 years, it has not taken off in terms of wide deployment. Some people are experimenting with, and it may find use locally in some limited scenarios. But in the meantime, ASPA, because it is similar to ROAs, and ROA deployment is progressing well, we can also imagine that people can start signing ASPA. It's just as easy once you have the infrastructure, you have the software for a validator, RPKI validator, etc. You can deploy ASPA in a shorter time frame. Yeah.
Thank you.
Okay, we have a question from the online queue from Jonathan Stewart from Manitoba Internet Exchange. Can you expand on what mutual transit means and how to define that in ASPA?
Okay, so some people, what the question is about, how do you define mutual transit and what does it mean for ASPA? Some people have used the word sibling for mutual transit, but we got advice from some network operators that mutual transit is a better term to use. That's why we are using that. But in any case, what it means is that there are two neighboring ASs and they consider each other as mutual transit. They share all the routes from one to the other, and therefore, each one of them registers the other as a transit provider. And by doing that, and they should be careful, not only one of them should not register, both of them, because usually they are, typically or many times they are the same organization. They should both register ASPA showing each other as a transit provider. And with that, in the algorithm, it is allowed. A route can propagate one of them to the right to the other, or the route can propagate from the other one to the left to the first one. So those routes would be valid. So that is why, I mean, that's the definition of mutual transit, and we take care of it in ASPA by having each of those ASs register the other or include the other in the ASPA as a provider. I hope that answers the question. So thank you very much.